Welcome back. Now I'm going to bring back the periodic table just one more time before we get loose. Now if you remember that I said that these Roman numerals from our week 2 discussion, that these Roman numerals play a shortcut and they are very handy, if you don't want to spend a ton of time writing electronic configurations. Unless you're specifically asked to write an electronic configuration, then yes, you do have to write it. But for the purpose of just learning the art of electronic configuration, we did learn them. Okay, so this means this is group 1A and group 2A. That means this elements that are under 1A can only lose one electron. Okay, now why is it loose? Because it's a metal. Okay, now hydrogen is an exception, but let's not focus so much on that now. Okay, now 2A, that means they can only lose 2 electrons. Okay, again, why it's losing? Because it's a metal. Okay, now remember we said when we talked about non-metals, especially the ones starting from 3A, 4A, 5A, 6A, 7A, and of course nothing can ever be done to 8A. But if we just focus just on these folks right here, these ones right here, okay, I'm going to switch to a different color, perhaps a blue. Okay, these are non-metals, right? These little bit of phase that I drew, okay, they gain electrons. Okay, of course boron is an exception. Okay, but again we don't want to get into it. Gain electrons, and how much they gain has to do with the magic number of 8. Okay, because that's the last one here. These are the noble gases. These right here are the noble gases. Okay, they are inert. In other words, all these elements have to look up to the 8 as a benchmark. So for instance, if we pick nitrogen, okay, which is 5A, okay, I think I've mentioned this once before, but I feel it's necessary to bring it back again. To get to 8A, okay, it needs 3 electrons because 8 is a magic number. It's known as the octet rule. Okay, 8 for octet. So that means it needs 3 more electrons to get to 8A. Okay, now here these are transition metals. Okay, these are unique, and when we learn naming, you would clearly see that in action. Is okay. Now with the alkali and alkaline earth metals, okay, they always lose 1, they always lose 2. Okay, alkali metals will always lose 1, alkaline earth metals always lose 2. But with the transition metals, which are all the way from here all the way up to zinc right here, okay, that's where the transition metals ends. Don't get carried away by the color. It's only from 3 through 12. Okay, that's where transition metals end. Okay, now these have what is called a variable oxidation state. Okay, again, this is a term I have not introduced to you, but I'm going to replace it quickly with another term, or variable charge. Okay, let me explain what that means once I get out of the periodic table. Okay, but while I have the periodic table, what I'm saying here is, let's say if we pick this chromium right here. Okay, I'm going to pick different color, maybe a black. Okay, if we pick chromium right here, it's got 6B, right? That means chromium can lose all 6 of its electrons, valence electrons, or it can lose 5, it can lose 4, it can lose 3, it can lose 2, it can lose 1. That means it can have a chameleon range of charges. Okay, that's what I meant by variable charges. Okay, so those are transition metals, and we probably will not get into too much discussion on the F block elements. Okay, so keep in mind, metals always lose electrons. I think I've mentioned this a countless times. Metals, okay, make cations. Okay, that means they lose electrons and they are indicated by a positive charge. See, nice summary of everything. Non-metals, okay, typically make anions, and they do so by, again there are exceptions, we will look into a couple of exceptions just to see how they are not always gaining. They can also lose electrons but don't gain any charge. So those are unique. Okay, gain electrons and they are carry a negative charge. This is the generalized version. Okay, this is typically is the case. Okay, generalized version. Okay, now as I mentioned earlier, for instance, chromium we said as a Roman numeral of 6A. Okay, this is a transition metal, so it's never going to gain electrons because metals always lose electrons. But because transition metals have a variable charge, okay, variable charge, that means chromium can lose all 6, which would lead it to plus 6, okay, or it can lose 3 and it will just be chromium 3 plus, or it can just lose 2, be chromium 2 plus. Now this right here, folks, is pretty bad. Okay, this is carcinogenic right here, chromium 6 plus. So, and similarly manganese I believe is 7A. Okay, and manganese 7 plus is pretty bad for the environment, and it can exist as manganese 2 plus, manganese 5 plus, etc. Okay, so these are all transition metals, so they have what is known as a variable charge, means it can exist in multiple oxidation numbers, also known as charge or oxidation states. They're all the same thing, it's just we use different terms in different contexts in chemistry, but they all mean the same. Okay, so an oxidation state, okay, an oxidation state is same as a variable charge. Okay, they are the same thing. Okay, not that it's going to affect your learning anyways, not one bit, but it's important that I make that connection. Okay, so we do establish the fact now metals make cations, non-metals make anions. Okay, so now let's jump into making compounds before we know how to name them. Okay, that's important because when you look at your Lay's chips ingredients or any other food material ingredients, there are a lot of chemicals which we may not be able to write a structure because some of them are much more complex, but there are also simple compounds we will learn in this class that you will see at that time. Say you're picking up a box of Lay's, one of those Pringles, and then you see sodium chloride on the back, you'd be able to write, most of you probably already know NaCl, but there's also other common chemicals that they use to treat those chips. So essentially you're eating a tube full of chemicals, so if you know what I mean. All right, so let's go and look at this PowerPoint that I created. It's also posted. Okay, so bonding, okay, that's very important. Okay, now there is no question of how is it relevant to my area of study. Okay, no matter what you are or where you are in your line of medical expertise, you never can get past bonding. Okay, now take ourselves. Our body is made up of, we got DNA. Okay, the DNA is made up of hydrogen bonding, and there's a complex bonding there, okay, between so many elements. Okay, just about every amino acids you pick, every protein you pick, there is bonding. Okay, so bonding is such a vital thing for us. Okay, so the food that we consume and the foods and the chemical compounds that naturally exist in our body, even they exist in some sort of bonding. Okay, we're going to look at three primary ones now, and then as we get more into the polarity of compounds and the concept map, we're going to talk about three more bondings at that point. Okay, but these are the most common ones that you want to know, but then there's three more that we're going to discuss in a different context. Okay, all right, with that said, okay, so bonding, to make a bond, okay, of any bond, okay, this is not James Bond but just a regular bond. To make a bond you need 2 electrons, okay, period. You need 2 electrons. And the three types of bonding we're going to talk about are ionic bond, a covalent bond, and metallic bond. Okay, I don't want to read through the screen, so I'm going to jump back into my screen tablet version here. All right, we've already made that very clear. You need 2 electrons, just like how you need 2 points to create a straight line, which is essentially what we're doing. 2 electrons are needed to create a bond. Okay, period. I don't think this rule is exceptional. Okay, you can have 4 bonds, but each will have 2 electrons. Okay, so for instance, if you take hydrogen gas, the one that's probably in your hydrogen fuel cars, which are still in vision, I don't think they have quite achieved where they want to be. So the electrons, each hydrogen gives 1 electron, okay, and you have a bond. Don't worry too much about it. I'm going to give you more details, but for now just follow along with me. Okay, don't think too much. Okay, and then oxygen is very vital for our living. O2, it's not O. Oxygen element is O, O2 is gas. Okay, you can also have liquid oxygen, but they are very expensive to make. Okay, they're beautiful, but they're expensive to make. All right, with that said, oxygen, however, you got oxygen and oxygen, but it's not single, it's double. But the point here is a bond can only have 2 electrons. Now we need nitrogen, N2, N2. Nitrogen is the most abundant gas in the mixture of gases that we see in the atmosphere. Nitrogen, however, has got a triple bond, unlike oxygen, which has double bond. Okay, now if you see, there's 3 bonds connecting 2 nitrogens, but each bond can only be made up of 2 electrons, no exception. There is no such thing as a single electron bond or triple electron bond. You could have triple bond, but you'll have a total of 6 electrons. You could have double bond. Now this is where its beauty, why you're in this class, is now your body, your blood contains hemoglobin, right? Heme, I'm just going to call it for now, heme. Okay, now hemoglobin is a complex molecule that involves a lot of bonding. Okay, but the key here is the heme contains iron 2 plus. Okay, iron 2 plus. Now people have tried to mimic artificial blood and oxygen interaction in lab, but they have consistently failed, because naturally what our body does is the iron 2 plus that's in the heme, okay, binds with the O2, okay, like this, with the oxygen, and it stays that way, and that's how the blood carries, okay, carries oxygen through the arteries to areas that's needed. Okay, This is a central phenomenon. Okay, if this doesn't happen, most of us are probably not getting oxygen in our blood, and it's not transported anywhere. However, what happens when people try this in lab to mimic it is, okay, this is natural, that's happening in us. Okay, this is a lab setting where people have tried to recreate heme with iron 2 plus, and then they interacted with the oxygen. Okay. Okay. All right. So when you do that, what happens here is, well, naturally the iron stays as +2. Okay, that is very, very important. But what happens in a lab setting is, the moment iron 2 plus comes in with oxygen, oxygen is a oxidizing agent, means it just pulverizes everything that comes in its way. It becomes iron 3 plus. Well, guess what, folks? This is bad. Iron 3 plus is nothing but rust. Okay, so fortunately this is not going to work unless we can keep iron 2 plus as iron 2 plus, which again people are not able to mimic. So there's sometimes we have to accept that there's things that we can just just create in lab and expect it to work. Okay, so now this has been unsuccessful since I was in high school. They've been trying this since 1994, 95, I would say. I don't think they've achieved this yet, because what they were thinking was, if they can replace the bad cancerous cells with the fresh ones that they inject, then they probably can get rid of cancer. But at least that was the bottom line. I don't know the full research behind it, but the point is they were not successful. Okay, so I felt this is important that you need to know this, because if you go to your biology class and your teacher talks about this, it will all make more sense. Okay, but the point here is, every bond has only 2 electrons. You could have double bond, triple bond, and then for instance cyanide. Okay, you all have heard of cyanide poisoning, right? That's a CN right here. I'm going to say cyanide. Okay, again, anything with nitrogen is triple bond. Anything it attaches to itself, it makes triple bond. That's the beauty of nitrogen. Now if you're going to like nitrogen, then you're going to have to be willing to share 3 bonds. Okay, now if you notice, all 3 bonds have 3 electrons, right? Now where am I going with this? All these are nonmetals interacting with the nonmetal, right? Of course, remember I said when I put it under alkali metals, hydrogen is actually not an alkali metal. It's only from lithium onwards. So hydrogen is actually a nonmetal. Okay, it's a nonmetal. Okay, so in all these examples you see here, our body does not obviously need cyanide, but it does needs everything else. Okay, so when the point here is, okay, when 2 nonmetals react with each other, okay, the resulting bond is covalent. Okay, that means if you have a combination of a nonmetal and a nonmetal bonded together by 2 electrons, that bond is called a covalent bond. Okay, covalent bonds don't have any charge. Okay, nor it will lead to any charges. So no charges, neither positive nor negative. Okay, now let's go turn our attention to a metal and a non-metal. Okay, and that's okay. So if you have a, say, metal and a non-metal, okay, oops, metal and a non-metal, then that bond is ionic. bond. Okay, and the metals typically carry a negative charge. Non-metals typically carry a metals carry a positive charge and non-metals carry a negative charge. Okay, what that means is, unlike covalent bond, okay, in a covalent bond, okay, a covalent bond, the two electrons are equally shared between the two elements that's it's connecting. The two electrons are equally shared. Keep that in mind, this keyword, equally shared. Okay, whereas in an ionic bond, okay, the electrons are not equally shared. Let's just leave it at that. Electrons are not equally shared. Okay. All right. Now let's look at a couple of examples, but I'm going to refresh my screen here as I'm getting close to 21 minutes on this video.